Cool. Okay. So I'm going to be the last one in between now and the drinks reception. So only 10 more minutes. Thank you for giving me those 10 more minutes. I'm Simon, and I'm very excited to talk to you about using AI to create biotechnology that helps us address some of our environmental challenges. So in my PhD, I work on designing AI algorithms that help us design and engineer enzymes to do chemical reactions. And enzymes are essentially small molecular factories that make and break bonds. And through that, they essentially reconfigure the atoms in various molecules and make all kinds of stuff and break it apart as well. And the two problems I concern myself with is optimizing enzymes so that a given enzyme is better at a particular task that it's doing, as well as finding new enzymes that do tasks that we can't yet do or don't know any enzyme for at the moment. And usually how we can most of the enzymes came about is through natural evolution. And you have many, many different enzymes in you all of the time. And I'm working on essentially giving evolution a leg up with the help of artificial intelligence, so we can accelerate it to get it where it needs to be to help us solve some environmental problems. But why, and how does climate change come into the picture? What environmental challenges am I even talking about? If you look at all the things that you see on this slide, as well as lots of the stuff on the chair that you're sitting on, the toothbrush that you brush your teeth with in the morning, all of the stuff that we use in everyday life, or a big majority of the stuff that we use in everyday life, has one thing in common, and that it's all made from oil and gas, and the atoms in it are reconfigured into the wonderful everyday gadgets that we use. And there's really two problems with that. The first problem is to actually do this reconfiguring of atoms to create the stuff that we use in everyday life requires a lot of energy, a lot of high temperatures and pressures to actually do the chemical reactions. But it also requires a lot of oil and gas as the input, because that's where we get the atoms from in the first place that we reconfigure. And so say we have all of the wonderful solutions that Anais and Petra developed for us with the electricity grid, and with everything renewable. Even if we can then do all of the reconfiguring of atoms, we still need to essentially get some feedstock, essentially feed in the original atoms that need to be reconfigured. And at the moment, that's entirely oil and gas. So just to give you a bigger picture of what this makes out in the global scheme of things, 15% of the global oil consumption, and I think 8% roughly of the global gas consumption, are used as input to reconfigure molecules to make the stuff that we use. So how can we do this in a more sustainable and renewable way, not using resources that are depletable? And for this, we can turn to nature, and nature does this all the time, and it does it directly with the molecules I already mentioned, with enzymes. Enzymes are proteins, and proteins are made up of 20 building blocks. And enzymes are a particular class of proteins that do chemical reactions, and you can see a comic on here. You see a little substrate going in. It performs an operation, and then it releases products. In this case, it breaks the substrate apart, but it can also fuse atoms together by creating bonds. And the special thing about enzymes is that they don't get used up in the process. They're essentially reusable. And this happens many, many thousands and millions of times every second. In your body, for example, you have an enzyme called carbonic anhydrase, which is in your blood. And carbonic anhydrase takes CO2 and water and turns it into bicarbonate at a rate of 1 million atoms of CO2 per second for every carbonic anhydrase molecule. And normally that would only happen at a rate of 200 per second. So you can see it's a very high speed up of how this reaction happens. So if enzymes are that great, why don't we make stuff? Why don't we do chemistry with them all of the time? And the real problem here is really a problem of price and volume. Creating enzymes at the moment is still fairly expensive. And so they are competitive up to about $50 per kilogram. So if we use enzymes to make chemical compounds that we can then sell for $50 a kilo or more, then they are competitive, and they are indeed used for lots of chemicals in the pharmaceutical industry already, because that's usually where you can charge these type of values per kilogram. However, if we talk about commodity chemicals such as fuel or plastics, those are often sold at $1 per kilogram. And so it's much more challenging to make an impact with enzymes there. And they also are sold at much higher volumes, so we need to create way more of them. And the problem then is we need to take the enzymes and make them efficient enough so that we can do that at scale. And going from, say, $50 a kilo to $1 a kilo is a very large jump. So you might wonder, is this even possible in principle? And these two guys have actually done it for a sample molecule for hydrogen peroxide. This is a medical doctor and a chemical engineer in Texas. 2016, they got together and founded a company called Solugen. And Solugen starts with an enzyme that they found in a pancreatic cancer cell of a patient. And they use that enzyme. This enzyme happens to produce hydrogen peroxide, and hydrogen peroxide is used for water treatment. It kills bacteria in water for hygiene purposes. It's used in lots of disinfectant. They scaled it up first in their garage in 2016 and made hydrogen peroxide. And at the time, they could sell it for $40 a kilo. And you can see here a float spar. These were actually their first clients because they were willing to pay $40 a kilo for plant-based hydrogen peroxide. But since then, they've scaled up the production process. This is a so-called bioforge, and they can now profitably sell hydrogen peroxide at a price of $2 per kilo. So we're now at the commodity range. And they've managed to do that by evolving that natural enzyme and improving its catalytic properties. How can we do this for other chemicals than hydrogen peroxide? How can we scale this to everything else? And this is where I hope my research can come in. This is and the first way in which I think my research can come in, and in the way that we can essentially improve natural proteins. And just to give you an idea of how large the combinatorial search space is, the typical enzyme, so enzymes are made out of 20 amino acids, the Lego blocks that you make them of, and the typical enzyme is about 300 amino acids long. So if you now picture a combination block with 300 dials, and each dial has 20 options, that gives you essentially the combinatorial search space that you have to search through. And that's way more than the 10 to the 43 estimated atoms that we think are in the universe. So we've got an enormous search space, which is all the green stuff on the slide. And nature has really only sampled a tiny fraction of it. So how can we help sample more of that? And the idea is to do that on a computer. And the way we did this in the lab is, and essentially tried out whether that could work in principle, is with a friend of mine in the biochemistry department who built a fantastic platform, a microfluidics platform, to test a couple of thousand variants in the scale of 2 weeks. And so what he did was he took a natural enzyme that performs a reaction, sampled about 10,000 mutations, local mutations around it in 2 weeks. And then I've taken his data set and performed the biochemical encoding. Unfortunately, the picture is very warped, but performed the biochemical encoding of the amino acids and performed and combined that with a language model predicting essentially the masked tokens of amino acids to get an idea of the grammar of proteins, what is in principle possible, to rank all of the possible single mutants around the starting enzyme. And Max has then taken the 5 best ranked mutants, synthesized them in the lab, and we found a mutant that was 4-fold improved versus the original starting point within essentially, and that is possible within the timescale of 2 weeks. Now, if you only do that with a single mutant, that amounts to turning a single dial on the combination lock, and that's obviously much smaller than the entire search space. So we've also expanded that to higher order mutants, and I'm happy to talk in more detail about the model we're using that in the drink reception. But the bottom line is, and unfortunately you can't see actually the results plots anymore, but through this process and by combining it with Max's domain knowledge, we managed to find a 16-fold improved enzyme, which if that reaction, this particular reaction is a test case, but if that reaction were a relevant reaction in the pharmaceutical industry or in the petrochemical industry, that would allow us to lower the costs by up to a factor of 16-fold. So this is improving existing enzymes. What if we don't have an enzyme to start with? And that could happen, for example, if we want to decompose waste, agricultural waste, to use it as the feedstock for our chemical synthesis instead of oil and gas. Or if we want to go even further and want to take CO2 directly from the air to take the carbon in the CO2 and use it to make all of the stuff around us. At the moment, we don't know very many enzymes that do that efficiently. And so we need to design new enzymes from scratch. And one technique that is popular in generative AI to design new samples from a distribution from scratch is diffusion modeling, and it's been popularized in the image space mostly. What you do is you take an image such as that of the computer lab, you add noise to it, and you train your model to predict what part of the kind of noised image is noise and what is image. And through that, you learn to denoise images. And when you then don't start from an image as a starting point, but from a noise, from a sample of noise, you manage to essentially generate new images. And you can translate the same idea to proteins and sample new proteins. And obviously, there's a few technicalities to do that. But the beautiful thing about these diffusion models in particular is that they allow you to condition whatever you design on certain properties. So the overall shape, substructure, and one of the particular things that we want to condition on if we design enzymes is also their dynamical properties. Because when enzymes produce their function, produce their chemical reaction, they actually undergo changes in the way they look. And so this is joint work with my PhD colleague in the computer lab, Yulia Komrovska, and we worked on an algorithm to take a subpart of a protein that we want to use that, for example, catalyzes a chemical reaction, as well as its local motion, and create a new scaffold for it, such that that subpart is still remains intact, but also moves in the same way, but now has a different backbone. And that allows us to have a different substrate specificity, so we can now use this enzyme. The idea is we can now use this enzyme for new input substrates. With that, I've given you the large-scale vision of where this is, where I'm hoping this is going to go. Commodity chemicals are, of course, a long stretch. We need to work a lot on that, but there's a lot of cool things that are very exciting for other environmental applications on the way. And I invite you to come talk to me at the drink reception to hear what they are. With that, I thank all of these superheroes I get to work with on a day-to-day basis, and you for your attention.
Okay, thank you very much. I see that we've already got a question here from